So these are the types of graphs you have used for your whole mathematical career to date. They're called rectangular or Cartesian coordinates. Look at them, just sitting there all square and boring. Don't you wish you could change that up somehow? What if we could do graphs that were circles? Well, guess what? That's what we're doing. It's called polar coordinates, and we're going to do polar functions. And as you might guess, it's very useful for describing things that have radial symmetry with respect to some axis, either three-dimensional or two-dimensional objects. You know, it could be just a circular object like a pizza, or a three-dimensional object like a sphere that's rotating, or a galaxy. It could be anything. See, that's the nice thing about math. It just represents anything at all. All right, so how do they work, these polar coordinates? So first of all, you need to be able to just plot points on them. And I put a sheet like this on the Google Classroom, but I didn't label it. I let you label it. So it's labeled the same way as the unit circle, right? 0, pi over 6, pi over 3, pi over 2, blah, blah, blah. And just like the unit circle, you have all the coterminal angles. And if we want to do a negative theta, we just go that way. Let's put one of that on one of my examples here. All right, so so we could go, so the typical way that we lay out the coordinates are r theta. So the r comes first. So for example, if I have the point 2 pi over 6, so I have these circles like this is 1, 2, 3, 4, 5, 6, 7, 8, obviously. So 2 pi over 6 is going to be right there. That's the point 2 pi over 6. All right, what else? 3 pi over 2. Here's pi over 2, 1, 2, 3. Here's the point 3 pi over 2. Okay, what if I have a negative value for r? So if you have negative value for r, you go to the angle and then go the opposite direction. So here's the point negative 3 pi over 2, negative 3 pi over 2. So I go to the angle pi over 2, but I run my r backwards away from the pi over 2 on the opposite side of the origin. So 1, 2, 3, here's the point negative 3 pi over 2, right? Where's negative 5, 0? Here's our angle 0. Negative 5 means we're going to go 5 units to the other direction, opposite the origin. 1, 2, 3, 4, 5. Here's the point negative 5, 0. All right? Yeah, we still call the point at the middle of the origin. How about negative angle, like 4 negative pi? Okay, where's negative pi? Well, it's the same place it is on the regular unit circle. I'm sorry, this doesn't all fit on here very well. Try to zoom here. Okay, so if I want negative pi, of course, instead of going this way, I go this way, and I end up in the same place. So here's 4 negative pi. Here's my angle negative pi. 1, 2, 3, 4. Here's the point 4 negative pi. So that wasn't very revealing. What about 5 negative pi over 6? 5 negative pi over 6. So we just go negative pi over 6, right? So you have the same coterminal angles as on the unit circle. So 1, 2, 3, 4, 5. Here's the point 5 negative pi over 6. So, obviously you have them both negative. Let's say we had, what does this go up to? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say I have negative 8 negative pi over 4. Well, look what they did on here. They didn't put the pi over 4s. Fortunately, they're right there. All right, so here's negative pi over 4. All right, here's positive pi over 4. Exactly between pi over 3 and pi over 6 is where pi over 4 is. So I want negative 8 negative pi over 4. So here's my angle negative pi over 4. And then I go to the opposite side of the, it's a little tricky to do. Right, here's negative 8, opposite side of the origin from here. Maybe it'd be helpful to use a ruler to do that, but probably don't really need it. So there's negative 8 negative pi over 4. All right, so you get the idea? That's how we plot things in polar coordinates. Now, the next thing we want to do, we're going to do a lot of things. We're going to do integrals and derivatives with it, functions, everything, like this week. A lot of it, like right now. But we're going to start with, there's a relationship between polar coordinates and rectangular coordinates. So I guess I'll write that as a title, a subtitle here. Relationship between polar and rectangular coordinates. All right, so it's pretty obvious. So you have a point xy that is Cartesian coordinates that we want to be able to convert back and forth between r, theta, which are polar. So rectangular, polar, how do we convert back and forth? Well, you already know because it's the same as vectors. Back down. There we go. It's the same as with vectors. So the r is just the distance from the origin, right? Whatever your r is how far you are from the origin. Well, that's the same as vector magnitude. So it's square root x squared plus y squared. So note that r is always positive in that. That's interesting. So if you convert to polars, if you convert from rectangulars to polars, you're going to default to a positive r. But see, there's lots of different ways to describe the same point. So, for example, is this the point 2 pi over 6, or is it the point negative 2, 7 pi over 6? Well, it's both. It's also, we go to 7 pi over 6 and go negative 2. So the problem you have is in polar coordinates, because everything's circular, every point has infinitely many representations. The same problem you have with the unit circle and coterminal angles. So what I'm just now noticing about this formula is it's always going to give you the positive r. Okay. And then your theta is going to be inverse tangent of y over x. But you have to pay attention to which quarter you're in. So depending on quadrant. All right, so, well, we'll do an example of that in a minute. And then if this gives you the r and the theta given x and y, and then, of course, x equals r cosine theta. This is how you go the other way, and y equals r sine theta. So there's a relationship between polar and rectangular coordinates. So, for example, if I had the point, let's do... trying to think of one that will give you a tricky angle to do. I guess let's do, negative 1, 1. So if I convert negative 1, 1 to polar coordinates, I mean, just really find the polar coordinate equivalent of the point negative 1, 1, right? So first of all, we're going to have r equals square root of 1 plus 1, so r is square root 2. I already squared them both, that's why they're both positive. And then you have theta equals inverse tangent of negative 1 over 1. So if I just were to do that on my calculator, inverse tangent of negative 1, so if I just do inverse tangent of negative 1, I get negative, that's pi over 4, okay, negative pi over 4, all right? So is negative pi over 4. All right, but there's a problem with that, because where's the point negative 1, 1 on here? So we're correct about the square root 2 being the distance. So square root of 2 is 1.414. So here's 1, here's 1.414, but we want to be on the pi over 4, right? Yeah. So here's the point. I'm trying to get this right here. Oh, here's another way we could do it, actually, to think of the point negative 1, 1. So think of a horizontal tangent to the circle, because this is y equals 1, and a vertical tangent to the circle, because this is x equals negative 1. Right there is the point we want. All right, so that's the point negative 1, 1 in Cartesian coordinates or in rectangular coordinates. All right, but if we say that the theta is negative pi over 4, we're going to be wrong, because negative pi over 4 is down here, and the point square root 2 negative pi over 4 is going to be down here. So this is what we mean by you have to watch the quadrant you're in when you get the theta. So this point negative 1, 1, I have to look and say, oh, it's in quadrant 2. That means that negative pi over 4, I have to add pi to it. So that negative pi over 4 is what we call a reference angle. So pi over 4 is like this angle. What am I going to use? One orange. This angle right here is pi over 4. So that means that the real angle that we're at is 3 pi over 4. So this is 3 pi over 4 up here, even though I've also marked it negative pi over 4. Oh, because it was a negative r. I was like, how? But that's not negative pi over 4. It's not, because negative pi over 4 is down here. The only reason that we have negative 8 negative pi over 4 over here is because the r is negative. So that pushes the point to the diametrically opposed side of the coordinate plane. All right, so hopefully that's sufficiently confusing. Our point negative 1, 1 is really the point square root 2, 3 pi over 4. Yeah. So essentially, we're going to look at this and we're going to say, okay, but theta equals 3 pi over 4 in quadrant 2. Right? So theta doesn't really equal that, would be another way to say that. Okay? There you go. So that's enough to convert points and angles. We'll do a couple of those next.